Representations of Boolean functions by real polynomials play a central role in theoretical computer science. This talk is about what I consider a particularly natural and important complexity measure called approximate degree. The notion of approximate degree was introduced 30 years ago in the seminal paper of Nissan and Szegedy. For a given Boolean function f, the epsilon approximate degree is defined as the minimum degree of a real polynomial p that approximates f pointwise within epsilon. This complexity measure is denoted deg sub epsilon of f, and as the definition implies, it is always an integer between 0 and n. The standard setting of the error parameter is epsilon equal to a third, which, of course, is without loss of generality. Over the past 3 decades, approximate degree has proven to be a powerful tool in theoretical computer science. Lower bounds on approximate degree are widely used in complexity theory, whereas upper bounds have various algorithmic applications. In particular, approximate degree has produced breakthroughs in quantum query complexity, communication complexity, and circuit complexity. On the algorithmic side, approximate degree underlies many of the strongest results obtained to date in computational learning, differentially private data release, and algorithm design in general. Approximate degree has been particularly valuable in the study of the class AC0 in circuit complexity. An AC0 circuit, pictured here, is any circuit of polynomial size and constant depth, made up of gates and or and not of unbounded fan-in. Here's our motivation slide again, this time with the results on AC0 highlighted in yellow. These include breakthroughs in quantum query complexity, communication complexity, and computational learning, such as the resolution of the quantum query complexity of element distinctness, the determination of the communication complexity of set disjointness in the two-party quantum model and number on the forehead multi-party model, and the fastest known algorithm for pack learning DNF formulas under arbitrary distributions. In view of these complexity theoretic and algorithmic applications, it has been an important open problem to determine the maximum approximate degree of an AC0 circuit. For circuits of depth 1, the answer was given by Nissan and Szegedy, who proved a tight lower bound of root n. This was the best lower bound for a while, until the breakthrough work of Aronson and Shi, who gave a lower bound of n to the 2/3 in their paper on the element distinctness function. Bunn, Thaler, and Kothari considered a generalization of this function called k-element distinctness, for which they proved a lower bound of roughly n to the 3/4. A big step in this line of work was taken 5 years ago in a beautiful paper of Bunn and Thaler, who proved a lower bound of n to the 1 minus delta for any constant delta. This essentially meets the trivial upper bound of n on the approximate degree of any function. Unfortunately, the depth of Bunn and Thaler's circuit is quite large. It grows with 1 over delta. If you try to flatten their circuit to depth 2 or to depth 100 for that matter, the circuit size blows up. The new size becomes 2 to the log n to the log 1 over delta, which is no longer polynomial in n. So the flattened circuit is no longer in AC0. All right, so this table captures the state of the art prior to our work. As you can see, there's a big gap in our understanding of the approximate degree for small depth versus large depth. This gap has persisted for the past 5 years with no techniques available to address it. In this work, we close the gap completely by proving that AC0 circuits of depth 2 already achieve essentially the maximum possible approximate degree of n to the 1 minus delta. Our approximate degree lower bound essentially matches the trivial upper bound of n that holds for any function, and our depth is best possible as well, because AC0 circuits of depth 1 have approximate degree only root n. In more detail, let delta be arbitrary, we construct an explicit DNF formula, f, in n variables that has constant width and approximate degree n to the 1 minus delta. Recall that the width of a DNF formula is the maximum size of its terms. In particular, our DNF formula is essentially as simple as it can possibly be. It has only polynomially many terms, and the size of each term is bounded by a constant. We also prove a refinement of our main result, where the error parameter is allowed to be vanishingly close to a half, as opposed to being a constant bounded away from a half. So let delta and c be arbitrary constants. We construct an explicit DNF formula f in n variables that has constant width as before and approximate degree n to the 1 minus delta, even for approximation to error a half minus 1 over n to the c. This error parameter is best possible because any polynomial size DNF formula can be approximated by a low degree polynomial to error inverse polynomially close to a half. Now, approximate degree is invariant under function negation, so all our theorems are valid for CNF formulas as well. Our main result has several applications, the first of which is multi-party communication complexity. In the standard model, known as number on the forehead, we have a function f with k arguments, each of which is a string of n bits, and k parties, which are numbered 1 through k in this figure. Each party is missing exactly one argument, which makes this model very powerful and extremely difficult to prove lower bounds in. The communication occurs in the form of broadcasts, and the parties additionally have access to a shared source of random bits, which they can use to decide which messages to send at any point in the protocol. They're required to compute f on every input with probability of error at most a third. The multi-party communication complexity of AC0 has been actively studied for more than 15 years. Our work finally closes this line of research. Let delta and c be arbitrary constants, we construct an explicit k-party communication problem f with randomized communication complexity at least n to the 1 minus delta quantity divided by 4 to the k. Moreover, our function is representable by a polynomial-sized DNF formula. We obtain this result as an immediate corollary to our main theorem on approximate degree. For this, we invoke the pattern matrix method, which transforms approximate degree lower bounds in a black box manner into communication lower bounds in various models. Our lower bound is essentially optimal and resolves the multi-party communication complexity of AC0. It shows that some of the simplest functions in AC0 already achieve essentially the maximum possible communication complexity. Prior to our work, the best construction was Bunn and Thaler's AC0 circuit of depth log 1 over delta. Another application I'd like to mention is quantum communication. Here we have two parties and a function f with two arguments. The parties communicate by exchanging quantum bits, and they're additionally allowed to share arbitrary prior entanglement before they start communicating. Their goal is to compute f with error at most a third on every input. Our main result essentially settles the quantum multi-party communication complexity, the quantum communication complexity of AC0. For arbitrary delta and C, we construct an explicit communication problem F with bounded error communication cost at least n to the 1 minus delta. Moreover, our function is representable by a polynomial size DNF formula of constant width. Once again, this result is an immediate corollary to our main theorem on approximate degree by invoking the pattern matrix method. Our lower bound essentially matches the trivial upper bound of n that holds for any function. Now, we have considered multi-party communication and quantum communication. If you combine these two models, you get the multi-party quantum model. All our lower bounds carry over to that model as well. Prior to our work, the best construction was Bunn and Thaler's AC0 circuit of depth log 1 over delta. All right, in the rest of the talk, I'll sketch the main ideas in the proof of our main result. To set the stage properly, I'll start by reviewing the approach of the previous best result due to Bunn and Thaler from 5 years ago. As the vast majority of other works on approximate degree, Bunn and Thaler's result is a form of hardness amplification. This means you come up with a procedure that takes an arbitrary function f and transforms it into a function with somewhat higher approximate degree. It's important that this transformation preserve membership in AC0. That way, if you start with an AC0 function, you get an AC0 function with slightly higher approximate degree. By applying this operation repeatedly, you can reach arbitrarily high approximate degree. Specifically, Bunn and Thaler start with an arbitrary function f in n Boolean variables and compose it with a carefully designed AC0 circuit of depth 3 with roughly n input bits. All right, this results in a composed function which I'm going to denote capital F. Bunn and Thaler show that if little f has approximate degree at least n to the 1 minus alpha, then the composed function capital F has approximate degree at least n to the 1 minus 2/3 alpha. By applying this transformation constantly many times, you get an AC0 function with arbitrarily large approximate degree. All right, now let's take a look at what's going on inside this big yellow box, which from now on I'm going to call the hardness amplifier. Bunn and Thaler start with an arbitrary function in n bits and compose it with this AND/OR tree. It's not hard to see that the resulting composition has approximate degree square root of m times larger than the approximate degree of the original function. This seems like good news, but unfortunately the number of variables has also increased by a factor of m. So really we haven't made any progress. However, Bunn and Thaler prove that this new approximate degree lower bound remains valid even if the input to the composed function is restricted to have Hamming weight roughly n. This makes it possible to compress the m times n bits to an input string of roughly n bits using a DNF formula, like so. This is Bunn and Thaler's hardness amplifier. There are two major bottlenecks here. Component-wise composition and input compression. They both require expensive circuitry, as a result of which the hardness amplifier is a depth 3 circuit that cannot be flattened without the size blowing up. To prove our main result, we cannot afford even a single iteration of the Bunn-Thaler hardness amplification. In this work, we design hardness amplification from scratch in a way that is unrelated to the Bunn-Thaler construction. Let me show you some highlights of our proof. We actually work in a more general setting. We start with an arbitrary function f that is allowed to have a very large number of input bits, like n to the 1000. Our assumption is that the restriction of f to inputs of Hamming weight n has approximate degree at least n to the 1 minus alpha. What this basically means is that f formally has n to the 1000 bits, but it is defined only if the Hamming weight is at most n. We compose f with a carefully designed DNF formula of constant width, which has roughly n to the 1 plus alpha input bits. Let capital F denote the resulting composition. We prove that the approximate degree of capital F is at least n to the 1 minus 2/3 alpha, even if we restrict the input to F, the input to capital F, to have Hamming weight roughly n. All right, there are two things happening here at the same time. First, the new function capital F has higher approximate degree than the original function. Second, capital F is denser than the original function in that capital F takes only n to the 1 plus alpha input bits. To summarize, we start with a very weak object, namely a sparse function with mildly large approximate degree, and create from it a much denser function with much higher approximate degree. This is a unique feature of our approach. Now, observe that if we start with a monotone DNF formula, little f of constant width, our hardness amplification produces another monotone DNF formula, capital F, also of constant width. By repeating this process any constant number of times, we're able to construct DNF formulas of arbitrarily high approximate degree. The big question is, how do we design the hardness amplifier? Since we're only allowed to use constant width DNF formulas, we cannot afford to use Bonn and Taylor's ideas of component-wise composition or input compression. We design hardness amplification from first principles. Here's how. The original function takes as input a vector of n to the 1000 bits, but at most n of them can be turned on at any one time. That makes it possible to view the input of f as the disjunction of n vectors, each of which is a coordinate vector or the zero vector. This change of representation has no effect on the approximate degree. To actually make it grow, we encode each of these new vectors as a string of n to the alpha bits. In this new picture, h corresponds to the decoding function, which takes as input a string of n to the alpha bits and produces a vector of n to the 1000 bits. The challenge, of course, is to design h such that h is hard for polynomials, but can still be computed by a DNF formula of constant width. That way, the approximate degree grows while the circuit remains small. Now let's take a look at some technical details. From now on, I'll let capital N stand for the total number of bits, and M stand for the input length for the decoding function. The decoding function h needs to produce either the zero vector, which we denote e sub 0, or one of the coordinate vectors, e1, e2, and so on. The requirements of h are as follows. First, as I mentioned before, h needs to be a monotone DNF formula of constant width. Second, the encoding of each e sub I needs to have constant Hamming weight. This is needed in order for the hardness amplification to produce a dense function in the end. Finally, the encodings of different e sub i's need to be indistinguishable by polynomials. Unfortunately, these three properties are too ambitious and cannot be implemented literally. What we do instead is achieve the third property with respect to appropriate probability distributions, lambda 0, lambda 1, and so on. And likewise, we prove the second property with high probability with respect to the same probability distributions, lambda I. All right, what are these probability distributions, lambda I? Well, let k be a large enough constant. We want the lambda i's to have three properties analogous to those of h. First, the lambda i's need to be concentrated on inputs of Hamming weight k. Second, each input of Hamming weight k must belong to the support of exactly one distribution, lambda I. And finally, the lambda i's need to be indistinguishable by low-degree polynomials. Once we have such lambda i's, we can define H to be the monotone DNF formula of width k that assumes that its input z has Hamming weight exactly k, and just checks to see which of the lambda i's has this input z in its support. All right, so this is a DNF of width k, which is a constant. The most difficult part, of course, is the construction of the lambda i's, which I will sketch next. We begin by constructing what we call a balanced coloring, where we color each k subset of the universe 1, 2, 3 through m with one of the colors 0, 1, 2 through capital N. To be balanced, a coloring must have the following property. Given any large enough subset A, the fraction of k subsets of A that are colored in a given color should be approximately 1 over n plus 1. We construct a highly balanced coloring using the notion of R discrepancy, which is a measure of aperiodicity or pseudo-randomness of a set of integers modulo a given modulus R. As our next step, we recall that the OR function on m bits has approximate degree root m. By linear programming duality, this implies the existence of a certain dual object on the m cube, which is a real function that has a large fraction of its L1 mass on the point 0 and is orthogonal to all polynomials of degree at most root m. If you visualize the m cube in this way, phi corresponds to this shading, where darker shades correspond to areas where the L1 norm of phi is concentrated. All right, let's scale phi down relative to the containing hypercube so we can move it around freely. If we pick a point z in this hypercube and shift phi to that point, we get a new dual object, call it phi sub z. This new object is, again, orthogonal to polynomials of degree at most root m, but its L1 norm is now concentrated at the point z as opposed to the origin. Now define capital phi I to be the average of the phi z's, where z ranges over all characteristic vectors of the k subsets colored with the ith color. With this definition, every point of Hamming weight k belongs to the support of exactly one capital phi I. It also turns out that for inputs of Hamming weight greater than k, the capital phi i's are almost identical due to the use of a balanced coloring. Now let capital phi denote this part that's common to all capital phi i's. Specifically, we define capital phi to be the minimum of the capital phi i's multiplied by the characteristic function of strings of Hamming weight greater than k. Then we define a probability distribution lambda I by this formula, and we verify the claimed properties of the lambda i's. This completes the proof sketch of our main result, and I'm going to end this talk with 3 of my favorite open problems on approximate degree. The first one is centrally related to this talk. It asks whether our lower bound of n to the 1 minus delta can be improved to a tight linear lower bound. The other 2 problems concern the approximate degree of 2 very natural and well-studied functions, both of which are motivated by quantum query lower bounds. And that's all I have.